So, this is chapter 14, and this is reaction rates. Yep. So the question is, how fast does a rate go? And does it go always at the same speed? Well, it doesn't, for a lot of reasons. First of all, it's important to note that reactions don't go in one single step. So when you put like A plus B, bam, C, no, that's not the way it happens, because you have two compounds that come together. And as we've already learned, compound A has to break apart. Compound B has to break apart. Then part of compound A matches with part of compound B and creates an intermediate. And then there's a catalyst. That, like, reactions are complicated. And so it happens in many different steps. I mean, just compound A breaking apart is a step. Compound B breaking apart is a step. And then, like, stuff has to happen in between. So there's a lot of things that happen. And each one of these steps has a rate. Now, remember, the second thing to remember is that rates are always set against time, right? A rate is set against time. If somebody says, at what rate is this happening? It's always per second, always per minute, always per something. There's always, it's always set against time, okay? And the next thing is that rates of chemical reactions change with temperature. Why is that? Well, first of all, they're exothermic or endothermic. So if you add energy or you take energy away, all of this is coming up. I'm going to explain all of this more. I'm giving you a very overview umbrella right now. If you add energy or you take energy away, that is going to change how fast the reaction goes. You also can add catalysts, which could change the rate. So rate can be changed, okay? So rates are very like persnickety little things. But there's equations that we use, and then we simplify it down to this is your first year of chemistry. All right? So that's what this chapter is about. It's your first year of chemistry, and you need to learn very basics of rate. So every time that you think that you have like this complex question, remember, you're learning the basics of rate. So we're going to learn the basics, then we're going to do free response questions and see how it all fits in. Okay? All right, here we go. So rate, the reaction rate is the rate at which the concentration and we represent concentration by square brackets. We know this, don't we, already? No? Okay. So concentration of any substance is represented by square brackets of reactants and products changes over time. So units of reaction rates would be sort of like, for example, molarity per second. Now, if we look at this, that would be like moles per liter seconds, right? Or a better way to look at it, moles per liter seconds. So this is basically the unit that we use, is moles per liter seconds, which is if you does that make sense? All right, moles per liter seconds. Got it? Everybody okay? All right. Concentration, so therefore, this concentration are in units of molarity. So when you see those brackets, we're talking molarity in specific. And reaction rates are presented as positive. And you will see why. Okay, so it's always like moles per liter per second. Like how far are they moving to the left, to the right? Moles per liter per second as positive. All right. Okay. So here we go. Rate laws. The basic rate law looks like this. The rate is equal to K times the concentration of, for example, NO2 to the lowercase n, where K is equal to the rate constant lowercase n is equal to the order, that's what we call it, the order of the reactant. It can be an integer, including 0. Or a fraction. Now, you won't really see fractions because we don't have time. Like, there's no time on the test to mess around with fractions. So you're just plain not going to see them. But it's important to note that it could be 0.67, like it could be 2/3, but it won't be. A huge note. Concentrations of the products are not included in the rate law. Because why would they be? They do not affect the rate of a reaction. Also, N must be determined by experiment. It is not with lots and lots of underlines and exclamation points, the coefficients. And the reason I say that is because in its simplest form, the rate law looks like n is the coefficients. And since we are at the very beginning, like chapter 14 is like very simple rate law stuff, often n is going to be the same number as the coefficient. It is not the coefficient. We are actually going to determine what m and n are by experimental data, and it's only going to be coincidence that it turns out to be the same as the coefficient, okay? And when we do the next chapter, which is on solutions, those exponents are, in fact, the coefficients. So this is very confusing, But in the rate law, it is determined by experimental data. And on the AP exam, I want to be clear, on the AP exam, you will be determining these coefficients from experimental data. It is part of what I am teaching you to do. That is what is part of the free response questions on the AP exam. There's only like 3 things you do with rates on the AP exam, and that is one of them. The other one is determining the order of an equation based on a graph, and the other one is determining half-life, which is a first order, solving for half-life, which is a nuclear half-life, which is a first order equation, using the equation. All right, there's only 3 or 4 things you do. Very simple stuff, but you got to get it. All right, and it's very simple. Okay, here we go. So there's 2 types of rate laws. And most of what we do is one type, but we do a little bit of work with the second. The first is the differential rate law. That's an I, differential. And this is commonly what we call the rate law. And this is where the rate depends on concentration. Now, what this means is that as the concentration drops, the rate slows down, right? Because there's a whole lot. It's, imagine imagine trying to make Girl Scout cookie sales. And so you walk into a room with 350 people and you set up your table. You're going to be barraged by people who want Girl Scout cookies. And then slowly those people move into their conference, let's say, they're going into the next room, into their workshop, right? And now there's only like 50 people left in the room. How are your cookie sales doing? Not as well. Why? Because there's not as many people, right? The concentration of people is much lower. See that? So same thing, differential rate law, right? High concentration of reactants, then the rate is really high. Then everything shifts over to the product side, the rate starts to slow down. Why? Well, there just aren't as many molecules of reactant to bang into each other anymore. The concentration is lower, so the rate slows down. So this is differential rate law. Depends on the concentration of the reactants. Okay, number 2, the integrated rate law, which we don't do much with, but we do a little bit, but not much. Concentrations depend on time. So you can imagine right away when you hear this, you see 2 different graphs, right? One is concentrations versus time, y versus x, concentration versus time, and the other one is rate versus concentration. Okay, so there's 2 different graphs involved here. All right, so let's keep moving. Okay, so the next one is determining, we're going to start working with the differential. Okay, so the equation used to determine the reaction rate is this. Rate equals K times the concentration of A to the X times the concentration of B to the Y. K equals the rate constant, It is a fixed value for each reaction. So it's reaction specific at a particular temperature. So in other words, you have to look it up or be given it or calculate it, but you cannot guess it, you cannot know it. Now, most of our reactions are going to be done at 25 degrees Celsius. So most of the stuff that you're going to receive is going to say at 25 degrees Celsius, and then it's going to give you the K, right, in the So since this K is at a very specific reaction for a very specific temperature, they have to give you all the information that you need. That doesn't mean they're going to give you X and Y or A and B, but they have to give you enough so that you can solve for everything, all right? X and Y, now remember, I told you they are not the coefficients, right? Are determined experimentally. You're going to get data, and I'm about to give you, like, we're about to do some problems, right? Determined experimentally. And they are not coefficients. I write this over and over and over, and we still, because it's coincidental, and then people get lazy and they just write down, oh, no, it's the coefficients, all right? And then the concentration of A and the concentration of B are the molar concentrations of the reaction, of the reactants. Only in moles per liter. Molarity, right? All right, so here's your first example. So okay. So example 1. Here's the equation. Nitrogen dioxide gas plus ozone yields nitrogen trioxide gas plus oxygen. So this is the equation for the breakdown of ozone. O2, sorry, O2. Thank you, O2. There we go. Okay, thank you. All right, so my rate equation here is going to be the rate is equal to K times the concentration of NO2 times the concentration of O2. I'm telling you this. This isn't a mystery. This is given. O3. So I'm going to put this here. Given. Okay, so it's given. So you're not like, is that like, why? No, it's given, right? Okay, now what does this mean? So that means, just so we're looking here, X and Y are what? 1, right? Okay? Everybody with me? All right. So what does this mean? So this means that if I double the concentration of NO2, right? The rate doubles. So let's look at the math here. Okay? If NO2 is X, and I double it to 2X, with the exponent at 1, I literally did not change it because it's still 2X. Everybody understand? So my rate went up by a factor of 2. Is everybody with me? Okay, now, what happens if, and I'm going to do this now, and then I'm going to do it again later because it gets confusing. What happens if it's squared, like X is 2, okay? And so my NO2 concentration is X, and now I double X. You with me? Now what happens to my rate? Yes, it goes up by a factor of 4. Do you see that? So first of all, I want to be clear about something. First of all, if you know that it's a 2, then you can say, well, if I double it, my concentration, my rate will go up by a factor of 4. But if you don't know it's a 2, but in the experiment, you have data that tells you I doubled my concentration and my rate went up by a factor of 4, then you know that your exponent is a 2. Yeah.
So the x wouldn't be squared.
If I double the rate, then the rate doubles, then my exponent is 1. That's what that says. Okay? Because if what I do, it does the same, then the exponent is 1. Okay? Mm-hmm.
Part right here, part of the given that if I double NO2, then the rate.
No.
No. Then where,
Okay, so
like, is that just because?
it's a math, it's just a math. If I double it.
Right. But, okay. Whatever.
So, no. If the exponent is 1, then if I double my rate, if I double my concentration, the rate doubles. If I increase either one, by 5x, then the rate increases by 5x. So in other words, because my exponent is 1, whatever I do to my concentration, the rate will follow that because the exponent is 1. So I'm presenting you with this equation and saying, since the exponent is 1, the rate will follow the increase of the concentration. If you were to see lab data where the rate follows the increase of the concentration, you will know that the exponent is 1. Okay? And the reason I say this is because you're going to be given experimental data and you're going to have to find the exponent. All right? Okay. So first order reactions, that's what this is called. First order reactions. Where X and Y are 1. Okay? With rate changes.
I'm sorry. Is that x plus y equals 1 or
X and
is 1
Y.
and y is 1?
Directly proportional to concentration changes. Okay, so now we're going to take a look at some second order reactions. Okay, here we go. Okay, second example. Two NO, 2 nitrogen monoxide gas, plus O2 gas yields 2 NO2 gas. All right, so the rate, sorry, there you go, sorry. Rate is equal to K, there's my constant again, nitrogen monoxide squared, oxygen to the 1. This, again, I am giving you this rate equation. It is given. You do not, there's no reason that you would know what it is. I am giving it to you, okay? So now let's discuss what it means. So if I double the concentration of the O2, it has an exponent of 1, so the rate doubles. We call this first order. That's what it's called, first order. The reason is because it has an exponent of 1. It's called first order. It's a first order reaction, okay? First order with respect to. I'm going to give you that quote. We say, this reaction is first order with respect to oxygen. Okay? If I double the concentration of NO, the rate increases by 4 times. And the reason is because the concentration of NO has an exponent of 2. We call this second order. So we would say, this is how we would say it. Reaction is first order with respect to O2, second order with respect to NO, nitrogen monoxide, and third order overall. And the reason it is third order overall is because first plus second, third. Like 1 plus 2. Right? 1 plus 2. We add them together. All right? Which means that if we doubled all 3 of them, it would go up by a power of an exponent of 3. If you doubled the first order and then you doubled the second, it would go up by an exponent of 3. Okay? All right. Here we go. Here's your first problem. So, here's your rate. By what factor will this rate be raised? If hydrogen iodide is raised from 1 molar to 4 molar. So, because this is squared, we're going to increase this by 4, which means it's going to go up by 16. Because it's going to be squared, right? Everybody okay? Okay, next. All right. Now, here we go. This is what you're going to get. You're going to get experimental data. And what you need to do is figure out what order, what the X and Y are for each of the concentrations, and what order they are, and then what order it is for the whole equation. This is how you do it. Super easy. You start by noticing that there are 3 trials, and 2 of them for A are the same, and 2 of them for B are the same. So let's start with A, the concentration of A. When I double A, B stays the same. So when I double the concentration of A, since B stays the same, the rate goes up by 4. When I double the concentration of A, the rate goes up by 4. So what's the exponent? It's a 2. So X equals 2. When I double the concentration, when I double the concentration of A, wrong one. When I double the concentration of A, B stays the same, right? The rate goes up by 2, right? When I double the concentration of B and A stays the same, it goes up by 4. So that means that X is 1 and Y must be 2, right? So now I pretty much have this, right? Rate equals K times A to the 1 and B to the 2. How did I determine that? Experimentally. You with me? Now, can I solve for K? Yeah, I can. Gino, are you nodding like yes, you can? What can I do? You were saying, oh, okay. Yes, I can. Any one of these rates will work, right? Any one of them. And I have concentrations. So let's do it. So let's plug in. I'm going to take this one in the middle. I'm going to take my rate, 4.00 times 10 to the minus 3. That's my rate, is equal to K times my concentration of A, 0. See what I'm doing? Right? To the 1 times my concentration of D, so 100 to the 2, and I'm done. And now can I solve for K? Yes, I can. At this temperature, for this reaction, this will solve for my K. Okay? You're going to get a lot of these. Not as many as you're going to want, but you are, because you're going to want more, because they don't, it's like, you know, oh, they have 5 of them, and what you really want is like 10 of them, you know what I mean? But I can get more from other books and stuff. But this is one of the things, this is an AP question. This is one of the things you have to do on the AP exam. Okay? All right. Here we go. Ready? Your turn. This is your turn. What is the order of the reaction with respect to nitrogen monoxide and respect to chlorine? Whoops. Sorry. Are we ready? Okay, so these are the same. So when I double, let's start here. These are the same. So when I double nitrogen monoxide, my rate goes up by 4, right? So for nitrogen monoxide, NO, it's a 2.
0.35 times 4 is 1.4 though, not 1.4.
Close enough. Remember, this is experimental data, right? So it's close enough. Next, and that's the lesson here, actually, right? Next, these two stay the same, and when I double the Cl2, again, close enough, right? Okay, so Cl2, good. So now, my equation, first order, second order for NO, and the concentration goes up by 2. So here's my rate. Rate equals K NO squared Cl2. Now, can I find K? I sure can, right? If I need to, because here's my rate. Notice rate set against time. Sorry, concentration set against time, right? Okay? All right, moving on. All right, so we're going to stop here, and your homework's going to go up on Canvas. So you want to look up on Canvas, okay?